Alright, today we'll be looking at depth first search. Let's look at a graph first. If we start at vertex 0, and if we perform a depth first search algorithm, we will try to go as far as possible, and when there's nothing new to discover, finish the node and retrace your steps to find something new. It's a bit similar to the concept of exploring for breadth first search, but we call it discovering and finishing a vertex. So we're going to color it purple for discovered and orange for finished, similarly to what we did with breadth first search. So the first vertex we're given is vertex 0, so we discovered it. Now we'll try to go as deep as possible, so looking at our neighbors, we see vertex 1. So instead of finishing 0, we're going to visit vertex 1 right away and discover it. Now we're at vertex 1, and then we do the same thing. We try to go deep. So we found vertex 4, we immediately go over there and mark 4 as discovered, and then again, so you get to vertex 5 and you discover it. Vertex 5 only has 4 as a neighbor, but it has already been marked as discovered, so there is nothing new to discover. So that means we finished 5, so it's orange now. Once there's nothing new to discover, we retrace our steps to find something new. We go back to 4. 4 still has neighbors that are undiscovered, which is vertex 6, so we hop on there and discover it. Vertex 6 has no more neighbors that are undiscovered, so we have finished vertex 6, so we retrace our steps and we go back to 4. Now 4 no longer has undiscovered neighbors, so we are finished with 4 and now we backtrack. Now we are at 1, so I think you get the point. The biggest difference between BFS and DFS is the way they discover the nodes. DFS likes to go all the way to the end and finish the nodes. BFS likes to finish exploring the vertex right away and work their way to the end. So let's go a bit faster. Vertex 1 still has a non-discovered neighbor, so we go to 3. We mark 3 as discovered and we see that we have an undiscovered vertex 2, so we go over there. We discover it. There are no undiscovered nodes around vertex 2, so we finish it. Now we retrace our steps, and one way to remember which node you were on before is to think of the discovered list as a stack on the top right corner. You can imagine the gray nodes are not there, and you basically form a stack with the colored discovered nodes. So which node would you retrace back to? Yes, that's right, it's node 3. So nothing else to do with node 3, so we finish it. Now we look at our discovered stack. The top is node 1, so we go back to node 1. Nothing else to do with node 1, so we finish it. And then our last node, which is actually our original node, the first node we discovered. So we finish that too, since there are no more undiscovered nodes, and voila, we are done. So quick things to note. As I said before, you can think of the discovered nodes as a stack you can use to retrace your steps. I left the gray nodes so that you can remember which nodes were discovered first. And then you have the finished nodes. And as you can see, the order of the finished nodes is definitely not the same as the ones discovered. As opposed to BFS, the ones discovered and the ones that are explored are the same. Okay, so how do we implement this? You've actually done this before, and it's similar to searching a tree. Basically, we are going to write a recursive function to perform depth first search. But before writing the recursive function, I'll show you what the function call stack is doing to illustrate your program. When we first call DFS, it will be on the first node of your graph. So let's just add that to the function call stack first. First, you want to mark your node as discovered. Then you want to iterate through all of your neighboring nodes. You check if that neighbor has already been discovered. If it's not discovered, you recurse on that node and do the same thing as what you just did with the original node. But if it's discovered, then you just skip it. And that's pretty much it. See how whenever there's a new call for DFS, it adds to the function call stack, and when we finish the node, it's removed. With the property of a recursion, you know that it's going to go deeper into the graph, and once it reaches a dead end, it'll finish exploring the vertex and retrace back to find new nodes. So now that we know how to perform DFS and BFS, What are the pros and cons of each? Well, both of them have linear time complexity, which is O of V plus E, because we have to go through every node, and for every node, we have to check each edge. So we end up checking every edge and every node in our graph. The space complexity of BFS is O of V because worst case scenario, you have one vertex and all the rest of the vertices are connected to that one vertex. So your Q is going to be size V minus 1, hence O of V. The space complexity of DFS is actually also O of V. It's a little bit trickier to see because you didn't explicitly allocate any memory, but remember that if you do recursion, each time you call the function and go deep, the space is implicitly allocated on the function call stack. So the worst case scenario here, similar to a tree, is if the recursion goes deep all the way to the last node without ever retracing. So you'll have all the nodes in your call stack, which is O of V. For DFS, we might have to traverse through the wrong path before reaching the destination vertex. So we might go through more vertices than we have to. Similar to the previous reason, BFS is more suitable for searching vertices which are closer to the given source vertex, while DFS is more suitable when the solution is away from the source. However, since BFS considers all neighbors first, it might not be very good for creating decision trees for games like chess. DFS will go deep into a path, and if it finds a winning state, it doesn't need to go on and search for other paths. If you're trying to find a shortest path from a source node to a destination node in an unweighted graph, then BFS might be better because it'll reach the vertex with the minimum number of edges from the source vertex. But for most coding problems you'll encounter, most of the time it's a matter of preference. Alright, so that's it for graph search with both breadth first search and depth first search, and I'll see you in the next one.